So a Maclaurin series is the special case of the Taylor series. It just is with A equals 0. So Maclaurin series means the A is always equal to 0. So notice 0 is being plugged in. It's x minus 0, x minus 0 squared, x minus 0 cubed. So it's just the special case. So the same thing. Maclaurin series for sine. So just is implied what the A is equal to. That's the only difference. So we go through and find the derivatives. And usually 4 is the good number. And if it's a trig function, it'll always get us back to the original. If it's a sine or a cosine, we'll always wrap back into the original. So again, make your list of evaluating the functions at the A, which is 0. So f prime of 0 gives me 1. Double prime of 0 is 0, because you know sine of 0 is 0. Plugging in 0 here, I get a negative 1 and 0. Okay, so now I'm ready to put it together. So again, I'm always going to start by putting in the 0 term so I establish the pattern correctly. So then I have x minus 0 to the 1 power over 1 factorial plus 0, x squared over 2 factorial minus 1, x cubed over 3 factorial plus 0, x to the 4th over 4 factorial. Okay, get rid of the 0 term. So this just turns into x. That's gone, right? So it's gone, that's gone. Next term I have is this. So I have negative x cubed over 3 factorial plus, and then it keeps going. So I just have 2 terms, so I could, if I wanted to, go figure out the 5th derivative, right? The 5th derivative would be cosine of x. The 5th derivative at 0 would be 1. So then I would have plus 1 x to the 5th over 5 factorial. If I wanted to know what the next term was to help me to establish the pattern, dot, dot, dot. Okay, let's see. So again, I want, when I plug in 0, when I plug in 1, when I plug in 2, to generate these terms. Okay, so I see 3 things going on. I've got the factorial in the denominator, the x to the power, and then I've got these changing signs again. So let's start with the easy thing in the denominator. Remember, if I want odd, I want to use 2n plus 1. So this is odd, correct? So when I plug in n equal 2, 2n plus 1 will give me 5, and this is really important. You must put the parentheses there to say 2n plus 1 factorial. Plug in n equal 1, that gives me 3 factorial. Plug in n equals 0, that gives me 1 factorial, which is just 1. Okay, so let's get the x to the power. So this is going to be x to the 2n plus 1 power. So my last thing is to take into account these changing signs, right? It's positive, negative, positive. So remember, it's either going to be this or it's going to be this. I always just like to try this one first. If I plug in n equals 0, that would give me a positive 1. Does that work? It does, because the first term is positive. I like to verify by using the second one. If I plug in n equal 1, does that give me negative like it should be? It does. So negative 1 to the n works. All right, so let's do the same thing for cosine of x right now. So cosine of x is very similar. Cosine of x, let's go find our 4 derivatives. Second derivative gives me negative cosine. Third derivative gives me sine. Fourth derivative, because you know that how sine and cosine work, it always comes back to the first problem. So if it says Maclaurin, that means the A is 0. So cosine of 0 is 1. F prime of 0 is 0. Double prime of 0 is negative 1. 0 and 1. Okay, so let's put these pieces together. So first term is 1 plus 0x over 1 factorial minus 1x squared over 2 factorial plus 0x cubed over 3 factorial. And then last one, plus 1x to the 4th over 4 factorial. And it keeps going on. So let's rewrite it, eliminating the 0 terms. Okay, so it's nice to have 3 terms. That was why I generated one more term. It's nice to have 3 terms to make our pattern. Okay, so we have 3 things going on again. Looks like I have factorial in the denominator, x to a power, and changing sign. So again, I want to start this at 0. And I want, when I plug in 0 to get this, when I plug in 1 to get this, and when I plug in 2 to get this. Looks like I've got even numbers, and to get even numbers you want to use 2n. So let's start with that factorial in the denominator. So 2n factorial will give me the 4 factorial, the 2 factorial, and when I plug in 0, 0 factorial, remember, is defined as 1. Okay, so that takes care of that. Then I have x to a power, so that's going to be x to the 2n power, because n equal 2 gives me 4, n equal 1 gives me 2. Now I have to take care of that negative. So let's try negative 1 to the n. If I plug in n equals 0, negative 1 to the 0 power gives me positive 1. Hey, that works. Plug in n equal 1, I get negative 1 to the 1 power. That works. So there it is, Maclaurin series for cosine.